Okay, so I've prepared some solutions of some amines as directed on the worksheet. This first one is ammonia and water. The second one is butylamine and water. And you might be able to see it's not brilliantly soluble. It's got a kind of swirling, slightly oily effect in the water there, which I don't sure is showing up in the film. It's not brilliantly soluble anyway. And this one is phenylamine, and you can see that's even less soluble. I've had to heat it quite a lot, and even then it's made a kind of emulsion to it, so it looks quite cloudy. So you might like to have a think for yourselves about why there is this difference in solubility between these two, and why butylamine appears to be slightly less soluble than ammonia in the first place. A good recap for you. I'm going to add a few drops of indicator now, so that we can see the pH of these solutions. So this is the ammonia and water solution first of all. You can see from the colour change, it's very definitely a basic solution. Let's try with the butylamine now. Okay, again, similar colour change, so you can see that one also is a basic solution. And let's try with the phenylamine. Okay, now this one is less convincing because it's not as soluble, so it has a kind of greenish tinge to it. It's not actually neutral, it is slightly basic, so it's a slightly sort of bluish green, but you can see how the basicity of this one compares with the previous ones. It's had a little bit more. It's not helped by the fact that the phenylamine itself has got a yellowish colour to it, which is affecting how this appears. Okay, I'll try adding a bit more. You can see that it has got a greenish quality to it, but it's on the blue side of green, so it's slightly more basic than a completely neutral solution would be. Okay, second experiment now, and this is to try dissolving these amines into hydrochloric acid, and I want to see if they're slightly more soluble in the hydrochloric acid than they were in water. Now, we might expect that they should be, because obviously these are basic. We just proved that in our previous little set of experiments. So we're adding a base to an acid, and we're expecting it should obviously make a salt and water. So if I add some ammonia to this hydrochloric acid, it's not really much of a comparison, because to be honest, the ammonia is highly soluble in water in the first place. So you can see, well, it just looks like it's made a solution very easily. Now, the butylamine was a little bit swirly and oily looking before, so it'll be interesting to see how this one compares. I'll add some butylamine to my hydrochloric acid. You see it's interesting making some white smoky fumes in there. Okay, but this one, I've added quite a lot. It doesn't appear to have any of that oiliness about it. It's gone straight into solution there. So it is much, much more soluble in the hydrochloric acid than it was in the water. And finally, the phenylamine. Now this one was extremely difficult to get it to dissolve before. I had to heat it up quite well, and even then it made an emulsion. It looked very cloudy. So let's see how this one compares. You can see the real yellow colour of the phenylamine here as well. I'll drop it into the hydrochloric acid. Straight away you can see I had oily yellow drops before, but this time it appears to be much, much more soluble. It's less soluble than the others, admittedly, but it's still getting into their solution much more easily than it did before. So there we are, it's made a very pale yellow solution, and that's without any heating at all. So much more soluble in the acid than it was in the water, and that's because it's able to make this salt, which is then obviously ionic and can then dissolve. So I'm about to do the third experiment on the sheet, and this one involves using this copper sulfate solution. You can see I've already put it in the boiling tubes. Now, copper sulfate has got this very distinctive blue colour to it, and that's because the copper ions that are in there are surrounded by water molecules acting as what we call ligands. Now, you might not have done this in the other side of the course yet, so this might be a little bit sort of new and confusing, but by the time you get to the end of the course, it will be really helpful to reflect back on this practical. Now, a ligand is something that's got a lone pair of electrons that's available to form a dative covalent or a coordinate bond with the metal ion. So we end up with a copper ion in the centre with 6 water molecules clustered around it, using the lone pairs on their oxygen to form coordinate bonds with that copper. And while we've got that set up, it has this lovely blue colour to it. But the thing is, any other species that's got a lone pair of electrons on it has the potential to act as a ligand as well. So these amines obviously have got NH2 groups on them, and we know that the nitrogen on the amine will have lone pair of electrons on it. So there's capability or potential for these species to act as ligands rather than the water. And what we're hoping is that we'll see what happens when these things exchange as a ligand for water, and we'll see if there's a different colour to it. So I'm going to add some ammonia now to the first one. And you can see it's made a really different colour. Okay, there's a really distinct and rather gorgeous colour there. It's still made a solution, but it's got this really lovely deep royal blue to it, and that's a classic colour that goes with copper 2+ ion with ammonia ligands around it. Okay, so we'll have a go now at trying to add the other amines to the other ones and see what happens. So let's try butyl amine and see if that will act as a ligand as well. You can see, look, it clearly is, and we've got that's well, very similar, same even, really gorgeous deep blue colour to it. So all those water ligands have been displaced, and we've got something with the amine group on it acting as a ligand around the copper ion instead. It's subtly different colour. And finally, I've got the phenylamine that I'm going to try. Now this one might be a little bit tricksy because phenylamine, as we know, is not very water soluble, so I might need to heat this one. We'll see how we go. I think it's making a sort of slight greenish colour to it, but I think that's actually due to the colour of the phenylamine itself, which has a sort of yellowy colour to it, as you saw. Let's try heating it a bit and see what happens. Oh wow, it looks almost fluorescent. Let's try heating it. It's not brilliantly soluble at all. I think that's the best we're going to get. You can see it's got a really strong, lurid colour to it. It's definitely acted as a ligand. It's definitely formed something new there. It's questionable whether it's very soluble. In this final experiment, we're going to try a nucleophilic addition-elimination type reaction. So I've got the amine already in my boiling tube, so ammonia in this one, butylamine in this one, and phenylamine in the last one. And I'm going to try adding some ethanoyl chloride to it. So this is the work that you did in the carboxylic acid derivatives topic, but we're looking at it from a slightly different perspective now because our main focus is the amine rather than the ethanol chloride. Now you can see I'm doing this in the fume cupboard because I'm expecting it might make some fumes. I've not turned the fume cupboard on because it's so noisy and I don't think you'd be able to hear me on the film, so I might need to keep taking some breaks so that I can get some fresh air breaths. Okay, so this is adding to the ammonia. You can see all those white fumes immediately. It should be making an amide in there. And it's quite a vigorous reaction. I don't know if you heard it hiss then as it was getting so hot. I'll drop another drop in. Okay, I think that's enough. Okay, so I've turned the fume cupboard on in between to try to let some of the fumes from that escape and so that I can actually breathe some fresh air. And while I was doing that, I also felt the bottom. It's still quite warm now. And even though there's a very small amount of liquid in there, it's generated quite a lot of heat, so it's quite an exothermic reaction. Okay, I'm going to try now adding some acid chloride, some ethanol chloride to the next one, to the butylamine, and I want you to compare how vigorous the reaction is. So I'm going to be really cautious with this one, just one drop. Crikey, it makes me jump every time. I don't know if you heard that hissing and sizzling. Let's try adding another drop. But you can hear, I think, every time I add some of the ethanol chloride, it's making quite a sort of, almost like a banging noise, a sort of sizzling bang. It's getting quite exothermic in there, and you can see it's made a whole load of those white fumes again. You might like to have a think about what those white fumes could potentially be. I'm going to pause again while I turn the fume cupboard on so I can get some more fresh air, and then we'll come back to do the last one. We're ready to try the final amine this time. So this one is the aminobenzene, or phenylamine. Let's add a couple of drops of the ethanol chloride to this one. Okay. Now this one's actually, you can see, a slightly less vigorous reaction than we had in the previous one. Okay, still getting some of that hissing and sizzling. Okay. You might like to have a think about why it seems to be less vigorous. Again, this one's warm, but not as hot as the other two were.